Let us now consider an example. Suppose that a business person has a 5-week commitment traveling between Fayetteville and Denver. Weekly departure from Fayetteville occurs on Mondays and return from Denver occurs on Wednesdays. A regular round trip costs $400, but a 20% discount is granted if the round trip dates span a weekend. A one-way ticket in either direction costs 75% of the regular price. How should the tickets be bought for the 5-week period? Let us apply the OR approach to this problem. The first step is the problem definition, which has 3 key elements: the objectives, limitations, and alternatives. Pause the video and try this yourself. Can you identify the objectives, limitations, and alternatives from the given problem? From the question, we can identify that our objective is to reduce the total cost for the trip. So we can state that the objective is to determine the ticket combination based on the price of tickets that provides the least overall cost for all the trips. The limitations, as stated in the question, include the days of departure and arrival. That is, the business person should leave Fayetteville on Monday and return on Wednesday, that too of the same week. Or in other words, we can state that a round trip from Fayetteville to Denver should be made within the same week, or that a weekend should not be spent in Denver. Now, how many different ways can we purchase the tickets so that we can achieve our objective without violating the limitations? Keep in mind that the way the tickets are purchased do not necessarily reflect the way the person stays in these cities. The most simple and straightforward ticket combination is 5 round-trip tickets originating from Fayetteville on Monday and returning to Fayetteville on Wednesday of the same week. But is this the only combination that we can make? Consider the situation in which the business person purchases a one-way ticket from Fayetteville to Denver for the first Monday. That is, if we write it in terms of weeks and Mondays and Wednesdays of the same week, it would appear something like this. For the first week, a one-way ticket from Fayetteville to Denver is purchased. Then, on the Wednesday of the same week, they return to Fayetteville by using a round-trip ticket originating from Denver. That is, it would appear something like this. As this is a round-trip ticket, it will be utilized in the second week as well, when going from Fayetteville to Denver. A similar ticket can be bought in the second and third week as well. That is, a round-trip ticket originating from Denver in the second week that is utilized on a Monday in the third week to go from Fayetteville back to Denver. This can be continued for the fourth and fifth week as well. And finally, for the last trip, that is, in week 5, when the departure from Fayetteville is not required on the next Monday, a one-way ticket from Denver to Fayetteville can be used. As this is the second alternative, that is, 1 Fayetteville to Denver ticket, 4 Denver to Fayetteville to Denver round-trip tickets that span weekends, and 1 Denver to Fayetteville one-way ticket for the last week. Let us modify the second alternative by merging the first and the last one-way ticket into one single round-trip ticket. This is entirely possible because tickets just reserve a seat on the plane for a person for a specific day and time and do not need to be used immediately. So the third alternative becomes something like this. That is, 1 Fayetteville to Denver to Fayetteville round-trip ticket to cover Monday of the first week and Wednesday of the last week, and 4 Denver to Fayetteville to Denver tickets to cover the remaining trips. In this last alternative, we get 5 return tickets, all of which span the weekend. And from the information given in the question, this would allow us to reap maximum discounts. Can you identify any other alternative? If so, list them down so that you can analyze it during the solution phase. For this problem, the solution does not require advanced mathematics or complicated models. In fact, for the solution, we will just calculate the total cost for each alternative. Alternative 1 has 5 regular round-trip tickets that do not span any weekends. As from the question, each ticket would cost $400. So for 5 tickets, the total cost would be 5 times $400, which would turn out to be $2,000. For the second alternative, the first ticket is a one-way ticket. And from the question, it costs 75% of a regular round-trip ticket. So the cost for the first ticket can be written as 75% of the regular $400. Now the round-trip tickets span weekends, and hence there is a 20% discount on them. That is, the cost for each of such tickets is only 80% of the regular price, which can be written as something like this. And there are 4 such tickets. So to calculate the total cost, we will just take it as 4 times. Finally, the last ticket is like the first one. That is, it is a one-way ticket, and hence it would cost only 75% of the regular ticket price. Therefore, the total cost for the second alternative turns out to be $1,880. Now, for the third alternative, all tickets are round trips and span at least one weekend. Hence, all of them will have a 20% discount each. So for alternative 3, we can write the total cost as 80% of the regular price times the number of tickets that will be required. And from mathematics, this turns out to be $1,600. From these total costs, we can identify that the best alternative, which costs the minimum amount of money, is alternative 3. And it is the best solution among all the alternatives, hence it is the optimal solution. To validate this model, we might try to find other alternatives and determine if they give us a better solution. Finally, the implementation involves telling the business person the combination of the tickets to purchase. Let us consider another example. A homeowner wants to make a backyard vegetable garden. The garden should be rectangular in shape and fenced. The owner has enough material to build a fence of 20 meters. What is the largest possible rectangular area that can be turned into a vegetable garden? What are the dimensions of that rectangular area? Now the owner has only 20 meters of fence material and they want to make the largest possible garden using only that material. So our objective is to maximize the area of the vegetable garden. But the 20 meter of material restricts the dimension of our garden. The garden should be rectangular. That is, the length of all the sides of the rectangle, which is the perimeter, should be equal to 20 meters, which is the maximum amount of material available. So our first limitation is that the perimeter of the rectangle should be equal to 20 meters. Moreover, the length or width of the rectangle cannot be 0 or less than 0. So there is a second limitation, that is, the length and width of the rectangle cannot be negative. As for alternatives, there are several available for this problem. In fact, theoretically, there are infinite alternatives. This is because the length and width of the rectangle can be in fractions, which mathematically makes it possible to assume any value between 0 and 20. Such variable are quantities that can assume any real value, such as 1, 1.1, 1.00001, and so on are called continuous variables. Examples of such variables include height, weight, temperature, and so on. Continuous variables make it difficult, if not impossible, to find the solution by listing down alternatives like in the ticket example. So we need to make use of advanced mathematical concepts to solve such problems. Let us first translate this problem into a mathematical model. Let L represent the length of the garden and W represent the width of the garden. Our objective is to maximize the area of the garden, and the area is given by the formula length times width. Next, the first limitation is to ensure that the perimeter is equal to the length of the fence available. That is, the length, and width, that is L plus W plus L plus W, which essentially becomes twice of L plus W, should be equal to the maximum amount of material available. The second constraint is the non-negativity constraint. That is, the length and width cannot be negative or less than 0. So the model essentially becomes something like this, where we maximize the area subject to the two constraints that we have identified. This problem can now be solved using differential calculus. If you're interested, give it a try. Before we end this video, here's another question to test your understanding of the topic. I would like you to pause the video and attempt this question yourself before checking the solution.